right, pre-calculus 4.3 and 4.4 notes. These are dealing with geometric sequences and then getting into logarithms. So terms in a geometric sequence are linked by multiplication or division. When we talked about arithmetic sequences before, they are connected or linked by addition or subtraction. So now we're talking about geometric sequences, multiplication and division. So looking at this geometric sequence, what is the next term? So we have to multiply by what to get from 1 to 3? We multiply by 3. To get from 3 to 9, we multiply by 3. Okay, so the next term here would be 81 times 3, which would be 243. So our common ratio is the value that we're multiplying by. We never use division. We're always going to write it as a multiplication. So, you know, if it's divided by 5, we would really write times 1 over 5, okay, for our common ratio. So our common ratio here is a 3. That's what we're multiplying by to get the next term. And so now we're going to look at this next part, and it says, determine whether a sequence is arithmetic, geometric, or neither. So I need to see, can I add to get each next term, or am I multiplying or dividing? If it's neither, then it's going to be neither. Okay, so 3 to 6 could be multiplied by 2 or add 3. 6 to 9 is add 3. 9 to 12 is add 3. So this one is arithmetic because I'm adding. Okay. So this next one, to get from 25 to 5, I could subtract 20, or I would divide by 5. To get from 5 to 1, I would have to divide by 5 or subtract 4. So subtraction isn't going to work because it wouldn't be the same. Remember that when you're doing sequences, whatever you're doing between each term has to be the same. So this one here is divided by 5th, which is really times 1/5, and it's a geometric sequence. Okay, so for this next one, to get from 1 to 1, I would have to add 0 or multiply times 1. To get from 1 to 2, I would have to add 1 or multiply times 2. So you notice there's already no pattern here. It's different values. Okay, so that's going to be neither. Okay, this next one, to get from 4 to 8, and then 8 to 16, I'm multiplying by 2 each time. So this one is a geometric sequence. The next one, to go from 10 to 8, subtract 2, 8 to 6, subtract 2, 6 to 4, subtract 2. So I'm subtracting 2 each time. Addition and subtraction is arithmetic. And then this last one, to go from 30 to 29, I would subtract 1. Then from 29 to 27, I would subtract 2. 27 to 24, I would subtract 3. So it's changing each time, which means that this is neither. The formula to find a geometric sequence is this right here. A sub n equals A sub 1 times R, which is our common ratio, to the n minus 1, where n is the term and R is our common ratio. And then this is just an example of the sequences. So you get A sub 1 times R, A sub 1 times R squared. Okay, so that's what it winds up being. So that's why the formula is times that n minus 1. So it says, write the explicit formula for the geometric sequences. So we need to know our A sub 1 and we need to know our common ratio. So our A sub 1 is our first value of our sequence, which is 6. Our R is going to be what we multiply or divide by to get each subsequent term. So in this case, 6 times 2. That would be 12 times 2, 24 times 2. So our R is 2. So our formula then is A sub n equals our A1 times R to the n minus 1 power. Okay, and that is our final answer. So the next one here is 50. To get to 10, I have to divide by 5. To get to 2, I have to divide by 5. And remember, I said that we're never dividing. Okay, for our common ratio, it's always going to be a multiplication. So it's times, so it's 1/5 is what I'm multiplying by each time. Okay, our a sub 1, our first term we started with, is 50. So our formula then is going to be 50 times 1/5 to the n minus 1. Once we know that, we can use that to solve for different terms. Okay, so we know here that A1 is 3, okay, and that our ratio is 2. So our formula then would be 3 times 2 to the n minus 1 power. Okay, and it wants us to find the first 5 terms. So a sub 1 we know. A sub 2, we're going to plug 2 in here. 2 minus 1 is 1. 2 to the first power is 1 times 3 is 6. A sub 3, 3 minus 1 is 2. 2 squared is 4 times 3 is 12. A sub 4, 4 minus 1 is 3. 2 to the third power is 8 times 3 is 24. A sub 5, 5 minus 1 is 4. 2 to the fourth power is 16. 16 times 3 is 48. So then we can plug in different values and we can find that term. So if it told us to find the 80th term, we could plug 80 in for n and find what that value would be. The common ratio tells us a couple of things. The common ratio is greater than 1. That's essentially kind of like our a is greater than 1 in our exponential functions. Okay, it's going to show exponential growth. Okay, remember that this is not a in our common ratio for geometric sequence. This is r, but like I said, it's similar to that a being greater than 1. The common ratio is less than 1, then that means it shows exponential decay. Okay, the other thing that we have to talk about is how to find the sum of finite geometric sequences. Okay, so just like we were able to find the sum of arithmetic sequences, we can find the sum of geometric sequences. So this would be where we would take, so like this one here says find the first 10 terms. So you would find all 10 terms and add them all together. Okay, but there's a formula to do it so that you don't have to find all the terms. So this formula is the sum of the nth term, okay, or to the nth term, is a sub 1, our first term, times the quantity 1 minus r, the common ratio, and the common ratio is raised to the nth power. Then all of that is divided by 1 minus r. You guys need to be very careful when you're putting these in your calculator. The couple of things that I saw today as students were working on this is -3 to the 9th power or the 8th power does not equal -3 in parentheses to the 8th power. This one right here is taking that 3 to the 8th power and then plopping a negative sign on it. This one is multiplying -3 8 times. Okay, so you really have to be careful when you're using your calculator. If you're using your calculator, also this has to go in parentheses. This has to be, that doesn't necessarily have to be in parentheses, but when you're dividing, that bottom piece needs to be in parentheses. Otherwise, it's going to divide by 1, and then it's going to subtract that common ratio. So you really have to keep track of that. Okay, so here we see 4 times 0.3 to the n. Now, do not mistake this for the geometric sequence formula. Okay. This is our geometric sequence, but that does not mean that 4 is our first term. Okay, to find our first term, because they may have done other stuff to this, to find our first term, we have to plug 1 in there. So a sub 1, because we have to have it for our formula, equals 4 times 0.3 to the first power. Okay, so that equals 1.2. And now I'm going to use that to plug it in. So this is called sigma notation here. So this is the Greek letter sigma, and you'll see that a lot when you're finding sums. And that means this is the term we're starting with, and this is the term we're ending with. Okay. So here we're looking for the sum of the first 12 terms, terms 1 through 12. Okay, so I'm going to put S sub 12 equals my A1, which is 1.2, times 1 minus 0.3, and it's that 0.3 that's raised to the 12th power. Okay, not the entire 1 minus 0.3. Okay, I forgot to put that 1 in there. All over 1 minus 0.3. Okay, and when you plug that into your calculator, you get 1.7. So the next question is the same thing. It's asking for the sum of the first 10 terms. So A sub 1 is 2. We need to find our R. So 2 times what gives us 6? 2 times 3. 6 times 3 is 18. So our R is 3. So S sub 10 equals 2 times 1 minus 3 to the 10th power. Okay, and once again, that 10 is on just the 3, not the entire 1 minus 3, over 1 minus 3. And you should get 59,048. If you're not getting these answers, you're probably maybe forgetting to put this in parentheses in the denominator. So make sure you're doing that. Okay, this next one, the sum of the first 6 terms. So we're looking for S sub 6. Our A1 is 40 here. And here I'm dividing by 2 each time. But remember, I always write it as a multiplication. So I'm multiplying by 1/2. Okay, so that's going to be 40 times 1 minus 1/2 or 0.5 to the 6th power, all over 1 minus 0.5. And that's going to give us 78.75. And once again, make sure the denominator's in parentheses, otherwise you'll get 38 point something. So now we're going to move on to 4.4, which is still talking about exponents. So a logarithm is just an exponent. So we're really just working on writing exponents and undoing them. So we're doing the operation of to a power and we're undoing it. So b to the x equals a actually becomes log of base b, a equals x. So what happens here is these two change places and you add the log. Okay. So log 8, base 8, 64 equals question is the same question as to what power do we need to raise 8 to get 64? Okay, so that's all we're trying to figure out. We're trying to figure out what do we have to raise 8 to get 64. So this question mark here would be, well, 2, because 8 squared is 64. All right, so let's take a look at just writing each as either a log or an exponent. Okay, so on this one, these two change places and it becomes log base 2. So this 2 goes down there and I have 64 equals 6. Same thing, these two change places. So log base 4, this becomes my base to the 4th power. Oh, I kind of wrote that weird. So log base 4 equals 1. Same thing here. It's going to become log base 5 of 1 equals 0. Same thing here. These are going to trade places. So it's going to become log base 3, 1/9 equals -2. So I'm just changing these two exponent and what's on the other side of the equals sign. They change places. Okay, so this one right here, write each logarithm as an exponent. So now I'm doing the same thing. So these two change places, and now this becomes the exponent. So 10 squared equals 100. Okay, this one and this one change places. So this 5 is the base to the 1st power equals 5. 12, yeah, if I can write. 12 to the 0 power equals 1. Okay, all of those are correct. We know those are correct. We know that 12 to the 0 power equals 1. We know that 10 squared equals 100. We know that 5 to the 1st power equals 5. Okay, so now we're going to actually solve. So we're going to rewrite these to solve. Okay, so we're gonna do the same thing. We're gonna swap these, okay, and we're gonna say 9 to the y power equals 81. Well, 9 squared is 81, so y equals 2. Same thing here. We're gonna change it around. So we're gonna say 5 to the third power equals x. So we know that x has to equal 125. Okay, so here we have b. Okay, b to the fifth power equals 32. Well, what to the fifth power equals 32? It's 2. Okay, and if you're unsure, remember we learned that we could do 32 to the, using the little caret key, to the 1/5, and that would give us that fifth root of 32, which would be 2. Okay, so you can always do that. Okay, so here I have 3 to the y equals 243. So y equals 5. 3 to the fifth power is 243. Same exact thing here, okay? So I'm going to take 4 to the negative second power equals x, but remember, I don't like negative exponents. So we're going to change that as 1 over 4 squared equals x, which means x has to equal 1 over 16. Okay, this next one, b to the negative 3 equals 1 over 216. Same thing, I don't like negative exponents, so I'm going to change that to 1 over b to the third power equals 1 over 216. So now what to the third power gives me 216? That is 6. So we just want to know what b is. So b is 6. And when we're talking about logs, we talk about a common log. And a common log is a logarithm with a base of 10. Okay, so here you see it's log base 10. But we can actually write it without the log, the 10 on it. Okay, so anytime you see the base of a logarithm that's not written, it's assumed to be 10. So here, this is log. Okay, so this is really log 10 of 100, okay, equals x. So now we're going to say 10 to the x power equals 100. So x would have to be 2. Because x, or 10 squared, is 100. Same thing, so log base 10, 1000 equals x. So now I'm going to rearrange it. So 10 to the x equals 1000, and x would have to equal 3. Another logarithm that we're going to use quite frequently is the natural logarithm. So the natural logarithm is any exponential function with a base of e. So like e to the 4th power. Okay, e is actually a number. It is an irrational number, meaning it never ends. Okay? And that number is actually 2.718, blah, 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 blah. Okay? So 2.718 is what you should keep in mind. Okay, it's on your calculator. Okay, it is, let's see. So right there, you see that e to the x button. Okay, and then there's your log button too. We're going to use that in a few minutes too. Okay, oh, and ln. So ln here is your natural log. Okay, so e and ln are inverses. Okay, meaning they undo each other. And we're going to get more into that next time I see you at chapter 4.5. Okay, but you need to understand that this is called the natural log. Okay, these are natural logarithms. Okay. When you push that log key I just showed you on your calculator, it actually gives you log base 10. But we know that we don't always work with log base 10s. We can have anything there in that A spot. So we actually need to be able to change these to decimals to be able to work with them and solve sometimes. So we can always rewrite a log that's not a base 10, and we can solve it by rewriting it as log of this value here over log of the base. Okay? And then we're going to plug that into my calculator. So I'm going to go on ahead and I'm going to put a parenthesis and I'm going to do log of that 256. I think that was the number, yep. And 2 parentheses because I have that log, okay? And then I'm gonna divide it by log of 4. And I get 4. So my answer here would be 4. Right? And I can do that with anything. So if I had, you know, log base 2 of 38, okay, that would just be log of 38 divided by log of 2. And I would put it in my calculator. So log of 38 divided by log of 2, and I would get 5.24. So that value would be approximately 5.2. Okay, properties of logarithms are the exact same as exponents for the most part. So remember that if we were multiplying exponents, we were really adding those exponents. So same thing here. If we have log of some base and we're multiplying 2 numbers, that means that we can really do the log of that number plus the log of the other number. Division, same thing. So log base b of m divided by n. Okay, and then the last one here is log base b of some number to a power. So all that happens there is that exponent, that power comes to the front. Okay, so this says write each expression as a single logarithm. So we're combining them. So we're gonna change it from these long ones into shorter ones. Okay, so this one right here, so we have 2, they have the same base and they're being added. Okay, so if we're adding them, that means that we can really multiply those numbers. Oh, that's an ugly 3. So now I can simplify it even more though, and I can simplify it down to log base 4 of 32 times 2, which is 64. So this next one, they're both log base 5. Okay, so it's going to be log base 5, and it's subtraction, and subtraction means I'm dividing these 2 numbers. So 625 divided by 25, and that gives me 25. So that's going to be log 5, base 5, 25. Okay, so I'm just simplifying these. I'm not solving anything right now. The next one, log base 3 of 81 squared. All I'm going to do is bring this exponent to the front and rewrite it. Okay? That's all I can do right now. I'm not solving it. I'm not doing anything else. Okay? And this last one here, same thing. I'm not breaking it apart into this. Okay, I'm not solving it. I'm just simplifying it. So this 3 can come up here. So it becomes 3 log 5 of 1 over 5. Okay, and I could break it into 2 logs if I wanted and subtract those, but that's not what the goal was. The goal was just to simplify it and rewrite it as a single log. So that's all for 4.3 and 4.4. You guys have a great night, and I'll see you next time.